So we've spent the last several weeks dealing primarily with the structure of atoms. So we looked a lot at the structure of an atom's nucleus, how the protons and neutrons are arranged. We spent quite a bit of time looking at the electron configurations of atoms, so where the electrons situate themselves around the nucleus. And then we spent some time looking at the periodic table, learned things like the charge pattern, so how to determine what charge an atom will have when it forms an ion. So we want to combine all the things we've learned so far to now examine how atoms join themselves together, okay, so how they bond together. So this will be the topic of Chapter 5. So we'll spend this whole chapter looking at the different ways that atoms, ions, and molecules hold themselves together to form larger, more complex structures. So after we finish up Chapter 5 and have a good idea of how atoms hold themselves together in molecules, we'll then learn how to name these molecules in Chapters 6 and 7. Then in Chapter 8, we will begin to learn about chemical reactions. So that is what most people consider true chemistry. So when you start performing reactions to make larger, more complex molecules. Before we can do all that, we need to lay some basic groundwork for the ideas behind chemical bonding. So the first thing we want to discuss is a chemical bond. Okay, so a chemical bond is a semi-permanent attraction between atoms, ions, or molecules. So that term semi-permanent might seem a little bit strange to you. So we can't really use the word permanent because chemical bonds can be broken and reformed. So we use the phrase semi-permanent because they're not going to just break on their own. Okay, something has to happen to break these bonds. So typically they do hold atoms together unless there's some sort of outside force acting on that. So we also included atoms, ions, and molecules in this definition. So we know that an ion is simply an atom with a charge, but molecules can also become bonded to other atoms. So we'll think about the polyatomic ions that we learned earlier. So a polyatomic ion could fall both in the category of ions or molecules here. Okay. So we said that a chemical bond is a semi-permanent attraction. So now we need to look at the two different types of attractions that we will encounter. So the first of these we'll refer to as an intramolecular force. Okay, so the spelling of that is very important. So an intramolecular force is simply the attraction that holds atoms together within a molecule. So these are the forces that hold sodium and chlorine together in sodium chloride, are the forces that hold hydrogen and oxygen together in a water molecule. So these are the classic forces we think about when we think about chemical bonds. These are the first that pop into our mind. But there's also another category of forces that also fall into the category of chemical bonds. So intermolecular forces are the attractions that occur between different molecules. So the classic example of intermolecular forces would be hydrogen bonding that you likely discussed in biology class. So hydrogen bonding can occur between two separate water molecules, for example. So if we think about, let's just draw out two waters here. And we'll discuss hydrogen bonding a little later on. But just for the diagram here, the oxygen and hydrogen are held together by intramolecular forces. The two water molecules could be held together in some fashion by intermolecular forces. Okay, so we'll discuss that at great length later. Just be aware of the difference between intra and intermolecular forces for now. We'll also discuss dipole interactions and then London dispersion forces. So those are the three intermolecular forces that we'll discuss in this class. So we need to be aware of intramolecular forces, and we'll actually spend the majority of our time discussing these forces, the forces that actually form chemical bonds. However, we will rarely use the term intramolecular forces. For this, we'll typically just call them chemical bonds. But we'll use the term intermolecular forces quite often, and because of that, we'll abbreviate that IMF. So if I want to talk about intermolecular forces, you'll see it often referred to as IMF. So you need to associate those two. And don't get that confused with the first force at the top. Okay. So we listed out the intermolecular forces, and I guess we should have reordered the notes here. But now let's discuss the different types of intramolecular forces. Okay, so we said that intramolecular forces were the types of chemical bonds that hold molecules together. So there are really three major types of intramolecular forces. There are ionic bonds, there are covalent bonds, and then less importantly we have metallic bonds. So from this point forward, instead of referring to intramolecular forces, we will refer to the specific bond type that we see, the specific force that we encounter in a molecule. So let's go ahead and define each of these three bond types. Okay, so ionic bonds are the electrostatic attractions between two ions that result from the complete transfer of electrons. So I know that was a lot of words, so let's go ahead and look at what this might look like in an example. So let's just say we have sodium and chlorine. So we'll learn later how we know that sodium and chlorine form an ionic bond. But for now, let's just look at what an ionic bond actually is. So if I have sodium, okay, and we know that sodium has one valence electron, so we could write out the full configuration, but we see that there's only one electron in the valence shell. Then we might have chlorine that has 7 valence electrons. Okay? So we know that atoms want to have a full outer shell, so remember that it's easier for sodium to lose one electron and have a positive charge, and it's easier for chlorine to gain one electron and have a negative charge. So what happens is sodium completely transfers its electron to chlorine. So then sodium has a +1 charge, and chlorine, and I won't draw the 8 electrons around it, but they're there, has a -1 charge. So now the +1 and the -1 charges attract each other. So that is what we call the electrostatic attraction. So an electrostatic attraction is just an attraction between two charged species here, so two charged atoms. So the charges result from the transfer of an electron, but the actual bond or the attraction is just the attraction between the two charged species. Okay, so the next type of bond that we'll discuss is a covalent bond. So a covalent bond is typically the idea that most people have coming into chemistry of what a chemical bond is. So covalent bonds result from the sharing of electrons. Okay. So again, we'll look at this in great depth later, but let's look at a really simple example now of what a covalent bond might look like. So let's just say I have a hydrogen atom with a single electron, and I have another hydrogen atom with a single electron. So the electron configuration for each of these atoms would be 1s1, 1s1. So each of these need one more electron to have a full outer energy level. So what they do, each of these hydrogens share their electron. So we get something that looks like this. And so we can say they're sharing them. So these electrons are each orbiting both of these atoms. So we show this sharing by showing there is a bond between them. Okay? So each line or each bond that we show represents 2 electrons being shared. So these electrons are orbiting in a far more complex fashion than I'm showing, but they're orbiting around each of these atoms. So these atoms are sharing their electrons, and that's a covalent bond. So those are the 2 types of bonds that we'll discuss for the majority of the course, but there is a third type of bond. It's a metallic bond. And metallic bonds are a little bit different. We define them as a sea of electrons flowing around nuclei. So that's kind of a strange concept. So let's look at what this might appear to be. So I will just draw nuclei as these little positive charges. Okay, so we can have a nice structure of them. Okay. So whereas in ionic bonds, electrons were transferred, in covalent bonds, electrons were shared. In metallic bonds, electrons kind of freely flow around. Okay, so they have no set location. Okay, so they can flow around and be shared between the metal nuclei here. Okay, so be aware of kind of the basic definition of metallic bonds, and we'll discuss it a little bit more in a few videos, but for the most part we're going to stick with the ionic and covalent bonds for this course. And so if we think about the key difference between ionic and covalent bonds, really the only difference is whether or not an electron is transferred. Okay, so are the two atoms transferring electrons or are they sharing electrons? So if we remember back to the section on periodic trends, think about the term electronegativity. So hopefully you remember that the higher an atom's electronegativity, the greater its ability to attract an electron. Okay? So we know that some atoms really like to attract electrons. Some atoms really like to give their electrons away. So in order to determine if a bond is ionic or covalent, we really have to think about, well, do the atoms involved in the bond prefer to attract electrons, or do they prefer to give electrons away? So in actuality, there isn't really a clear-cut line between ionic bonds and covalent bonds. So it turns out the majority of bonds are some combination of ionic or covalent. So electrons likely aren't completely transferred, but they likely aren't equally shared. Okay, so there's some combination of those two bond types going on. So we'll simplify this eventually and learn a clear classification on how to define a bond as being ionic or covalent. Before we do that, I do want you to be aware that even though we might define a bond as being purely ionic, it's really not. There's still some combination going on there. So you see in your notes, there is a table at the top called the Pauling electronegativity table. So we learned in the periodic trends chapter how to determine which atom in a pair of elements had a greater electronegativity. And we still need to be aware of that. That's something you should be able to do. But now we have a table that quantifies electronegativities. Okay? So these numbers have no units. Okay, so they are based on fluorine, which has the greatest electronegativity, having an arbitrary value of 4.0. So all the electronegativities are based on fluorine's value of 4.0. This system was defined by Linus Pauling. He was kind of an interesting guy. He won the Nobel Prize in Chemistry and also the Nobel Peace Prize as well. But he is often most remembered for his incorrect proposal of the structure of DNA before Watson and Crick actually got it right. Anyway, that's another topic for another day. But we use these electronegativity values to determine what type of bond we have present in a molecule. So you have this little chart at the bottom of the first page of your notes. The first row of the chart is the capital E, capital N, so electronegativity difference. The next line is the percent ionic character of a bond, and the bottom line is the percent covalent character. So the percent covalent character row is left blank, but you can pretty easily go back and fill that in as 100, 95, 90, and so on. So we see if we pick two atoms, so let's just pick fluorine, and we can choose magnesium. Okay, so let's say we have a bond between magnesium and fluorine. Okay, and I want to decide, would this be an ionic bond or a covalent bond purely, or what percentage combination would I have for this? So let's look at the difference. So magnesium has an electronegativity of 1.2, fluorine has an electronegativity of 4.0. So we want to find the electronegativity difference here. So we see that the difference, we have 4 minus 1.2 is equal to 2.8. So if you check the chart, there is no perfect number for 2.8, but you see that it's between 2.19 and 2.54. So you could say that the bond between magnesium and fluorine is somewhere between 70 and 80% ionic. So that means it's somewhere between 30 and 20% covalent. So that means in a bond between magnesium metal and fluorine, that the electrons would be mostly transferred because the bond is mostly ionic. So where would the electrons be transferred to? Could we answer that pretty easily? Well, that should be a pretty simple question to answer, because fluorine has an electronegativity of 4.0, magnesium has an electronegativity of 1.2, so fluorine is good at attracting electrons, So the electron from magnesium would mostly be transferred to fluorine there. Okay, so between 70 and 80% of that bond could be classified as ionic character, and then there would be some sharing happening there, but not to a tremendous amount. Okay? So I know that's kind of a confusing concept to think about the bond as being some percent ionic, some percent covalent, or having a certain percentage ionic character or a certain percentage covalent character. I just want you to be aware that that is the true nature of bonds. Okay, so you'll never be asked to use this little percent ionic, percent covalent character chart. Once we get past this topic, what I'm more concerned with is that you do keep in mind that the rules that we'll discuss for ionic and covalent bonds aren't completely accurate. There's actually some sort of mixing of these two types going on. So with that being said, let's learn some more simple rules for determining if a bond is ionic or covalent in nature. Okay. So the typical rules that we have for determining if a bond is ionic or covalent hinge on whether the atoms bonding are metals, metalloids, or nonmetals. So hopefully you remember on the periodic table the metalloids you have memorized, or you have them circled somewhere. The nonmetals are up here, plus hydrogen, and you have the metals over here. Okay? So the basic rules we have for the type of bond that is formed is if we have a metal plus a nonmetal, we get an ionic bond. Okay? So there's no need to check the electronegativity table and say, well, the bond is 85% ionic. That's not necessary. If the bond is between a metal and a nonmetal, we assume it is an ionic bond. If the bond is between a nonmetal and a nonmetal, we assume it is covalent. Okay? So a bond between an oxygen atom and a nitrogen atom, for example, we would say that's a covalent bond. The nitrogen atom and the oxygen atom are sharing the electrons. A bond, for example, between sodium and chlorine, a metal and a nonmetal, we would say, okay, that's an ionic bond. The electrons are being transferred there. So then we could say a nonmetal plus a metalloid. I'll abbreviate that. We consider that to be a covalent bond. Okay, so something between a bond between silicon and carbon, for example, a metalloid and a nonmetal, we would call that a covalent bond. And then the last type, probably the easiest to remember that we'll discuss, would be a bond between a metal and a metal. You'd probably guess that's a metallic bond. Okay. So again, be aware that metallic bonds exist, but we're going to spend the majority of our time dealing with these two combinations right here, a metal and a nonmetal, and a nonmetal and a nonmetal. So if a bond is ionic, the electrons are transferred. That's all we need to worry about. So if you have a bond between potassium and chlorine, for example, it's a metal and a nonmetal. So potassium gives its electron to chlorine, and that's the end of it. The electrons are transferred. We have the electrostatic attraction, and we're good to go. But covalent bonds are a little bit trickier. So we have two classes of covalent bonds we need to look at. We have a polar covalent bond and then a nonpolar covalent bond. Okay? So let's define these. A polar covalent bond results from the unequal sharing of electrons. A nonpolar covalent bond results from the equal sharing of electrons. Okay. So there is a way that we determine this. In order to determine if a covalent bond between two nonmetals is polar or nonpolar, we use the electronegativity table. So this is where we will use the electronegativity values most often. So what we'll do for each covalent bond that we encounter is we'll find the electronegativity difference for the two atoms, and then using that number we'll determine if it is a polar or nonpolar covalent bond. So I'm going to give you some numbers, some ranges, that you'll need to memorize. But kind of take these numbers with a grain of salt, and I'll explain why in just a second. So the typical range that we use for polar covalent bonds, and I'll call this electronegativity difference. And there's a nice little chart in your notes to fill this in. We'll say it's between 0 and 0.4. Okay? So if you had a bond between oxygen and oxygen, for example, they have the same electronegativity. So when you subtract it, you get 0, and you would see that it's a polar covalent bond. So, excuse me, I wrote this backwards. I apologize. I flipped the two. So write this down here. This is a nonpolar covalent bond. I apologize for that. So the electronegativity difference for nonpolar covalent bonds, I've got to write this down, is between 0 and 0.4. So the example I just described for oxygen, I would make it a nonpolar covalent bond. So that means they're equally sharing electrons. So let's think about that for a second. So let's just say I have an oxygen atom and I have an oxygen atom. Okay? They have a covalent bond connecting them. So they are sharing the electrons. The electronegativity value told us how good the atoms are at attracting electrons. So if oxygens are equally good at attracting electrons, that means they will equally share the electrons. Okay, so that should kind of make sense there. So then for polar covalent compounds, we have between 0.4 and 1.8. Okay? So if we subtract the electronegativities, find that the value lies between 0.4 and 1.8, we could say that it's a polar covalent bond. So you might ask, well, what if it's exactly 0.4? That's the reason I said to kind of take this scale with a grain of salt. Because all bonds are actually some combination of ionic and covalent bonds, these are ranges that humans kind of just made up. So if you consult a different textbook or a different website, you might find a slightly different range. Okay, so this isn't a hard and fast rule, but this is the number range that is most commonly used in most textbooks. So now let's look at an example of a polar covalent bond. Let's look at a bond between nitrogen and fluorine. Okay, so if I look at the electron, or first let's back up. So I know that it's a covalent bond because it's between two nonmetals. So then I must determine, is it a polar covalent bond or a nonpolar covalent bond? So I check the electronegativity values. I see fluorine is 4.0, nitrogen is 3.0. So the electronegativity difference is 1.0, so it's a polar covalent bond. So that means these electrons in this bond aren't being equally shared. One of the atoms is hogging the electrons, for lack of a better term. So which atom is hogging the electrons? How can I determine that? Well, that's fairly easy to determine, because if you look at the electronegativity values, the higher electronegativity is better at attracting electrons. So fluorine would unequally share the electrons with nitrogen. So the electron, if I wanted to draw it as orbiting the two atoms, it would spend more time around fluorine, because fluorine is better at attracting that electron. So because the electron spends more time around fluorine, I could say that fluorine has a slightly more negative charge than does nitrogen. So it's not like sodium and chlorine, where sodium has an actual +1 charge and chlorine has an actual -1 charge. They have these formula charges, we call them, which is the whole +1 or whole -1, because it actually transferred the electron. The nitrogen and fluorine here aren't actually transferring the electron. They just aren't sharing equally. So we say that fluorine has a slightly negative charge and nitrogen has a slightly positive charge. So that symbol I drew is the lowercase form of the Greek letter delta. So we say a slightly negative charge and a slightly positive charge. So for every polar covalent bond that we have, one of the atoms in the bond will be slightly negative because it's attracting the electrons more. One of the atoms will be slightly positive because it is not attracting the electrons as much. So just be aware that you should be able to label which of the atoms in a polar covalent bond is slightly negative and slightly positive. We can't label a nonpolar covalent bond here as being slightly negative or slightly positive, because these oxygens are equally sharing that electron, okay, so we don't have to worry about that. So there is one other little case that we need to discuss. So occasionally you could have a bond between two nonmetals where you actually have something that most closely resembles an ionic bond. So if you have an electronegativity difference that is greater than 1.8, we call it an ionic bond. Okay. So that's a pretty rare case. So if you look at fluorine and boron, for example, so fluorine has an electronegativity of 4.0, boron has an electronegativity of 2.0, okay? So that's a metal and a metalloid, so we define it initially as a covalent bond, but then when we check, we see that the electronegativity difference is so great that boron would actually transfer its electron to fluorine, okay? So be aware there are exceptions to these rules up here, primarily between the nonmetals, metalloids, and nonmetals and nonmetals, that we do need to consult these little numbers that we learned to determine if a bond is ionic or covalent there.